Hi, good afternoon, everyone. My name is Angesh Anupam. I'm based in School of Technologies. I was trained as a control systems engineer, but now I'm working at interface of systems engineering and data science. If that confuses you, I'm sure after this talk you'll understand what I'm trying to tell you with the interface between data science and systems engineering. So I'm going to talk about complex systems. What is a complex system? The definition of the complex system is very simple. Any system which is a complex system, as simple as that. But why it's so interesting? It's interesting because of many reasons. Because the moment we talk about a complex system, we first have to understand about the various challenges which we encounter with any complex system. Typically, such systems have so much of non-linearities within the system. They are mostly dynamic in nature, and there are lots of uncertainties within the system. I can come up with a very interesting example. So we, as a human, we are a complex system. So if you consider a human body, it consists of various organs which are having different functionalities at its own level, where if you want to define the functionality of the entire human body, you have to bring them together. And that behavior at the system level is most likely going to be different from what you encounter at the individual organ level, right? So this is how we have to understand, these are some of the issues we have to understand before we start analyzing a complex system. Now, when we are dealing with a complex system, we first have to find ways to analyze the system. And to do that, computational model is one of the options. So what is a computational model? It's a way to replicate the behavior, the properties of a system using maybe a computer program through which you can simulate the properties of the system or the body. Now, to do that, there are broadly two approaches. One is a very, I would say, traditional way of doing that, which is process-driven model, where you go and look around the science behind the system or a process, and you try to use the governing equations to implement the model of the system. Well, in theory, it sounds very good. It's a very elegant way to do that. But the moment you're dealing with a complex system, it's not that easy. It's simply because the governing equations behind a complex system are not so easy it's not so obvious. So the moment you try to use that approach, you might end up getting a model which is not a very accurate representation of the system. So the other approach is to use data. Now, the moment I use the word data, you might be thinking that, is it the kind of data we use for any typical black box AI model? The answer is no. First, we need to understand what is a data in this context. So for instance, when I'm here, I'm standing in front of you and I'm presenting something, it's similar to saying that I'm emitting some kind of data. Based on the information I'm sharing with you, you can start making guess about me. You can understand what kind of expertise, what kind of subject matter I can talk about, what's my expertise, and so on. So the way the data-driven model is something where you look at the data generated from a system, typically a complex system, and then you try to use that data to find the model which can describe the system. But the interesting question is that when we're talking about data-driven model, is it just about forecasting the future state of the system? The answer is yes and no, both. Yes, because forecasting is always important. It has been important for various reasons. But when we are talking about complex system, we are also interested in managing and optimization of the processes within the system. It's similar to saying that, for example, if you can optimize the parameter of a system, you can, in a way, you have a control over the system. You can take proactive steps, and you can manage the system the way you want the system to behave. I can come up with one interesting example if this is kind of sounding too technical, and example I can come up with is of a typical supply chain, for instance. Okay, so we all know about supply chain, and if let's say we consider food supply chain, what does it consist of? So food supply chain consists of the processes, food production at the farm level, to the food we get on our plate in our dining room. And if you look at the various processes happening within the system, within the supply chain, you'll find that there's so many different processes, and there's so much of carbon emission happening at every different processes, right? Every single step. Now, let's say that you want to cut down the carbon emission at every single step within the supply chain. How do you do that? The one approach is to go and cut down the emission. That's one approach. But consider a food processing company, for instance. They can't afford to go and use this kind of approach, because the moment you start looking at the shutting down a process which is emitting carbon, you might end up compromising on various other KPIs. You also have to make profit. You have to survive, right? You have to compete with your competitors. So you have to find ways to optimize the parameters through which you can cut down the emission, but at the same time you don't compromise on the other variables of interest. So this is an example where you might see that how optimization could be relevant. It's not an engineering system, it's a very I would say supply chain is something which everyone knows and everyone understands how it is important, right? Now, I'm sure that by now you have kind of understood the notion and the underlying issues with a complex system. Now I'm talking about my own research contribution, where I'm interested and what kind of work my team is doing. I'm mostly interested in developing the algorithms which are capable of deriving gray box model of complex system. Now, when I'm saying that, you might be thinking, can't we have one master algorithm which is capable of deriving a model for every system? The answer is no, because one size fits all approach doesn't work here. Every complex system is different, has got its own complexity. So my interest is mostly in quantification of the uncertainty, modeling of the uncertainties within the system, modeling of the noise, because when we are talking about data-driven model, every data comes up with some measurement noise, and we can't consider those noise every time, right? So the best way is to come up with the model. So my interest is in developing those kind of algorithms. And on top of that, we are also working on the application of these models for various types of systems, such as wetlands. We are also working on some the systems where we can design a material which is capable of producing or generating the carbon-free steel, I would say. There are different applications which you can think of. But in short, I would say that when we are talking about complex system, we have to understand that we can make it simpler, but we can't make it simpler beyond a point. And I would like to end my talk with a very good quotation from Albert Einstein, who said that everything should be made as simple as possible, but not simpler. Because the moment you try to become more simpler, you might end up compromising with the relevant properties of the system. So in short, as a concluding remark, I would say that complexity matters. We can't get rid of it. We have to live with it. And data is the key to unlock the complexity. Thank you.